Hi, in this lecture, we're going to introduce in a little bit of vocabulary. So we'll define a first order ordinary differential equation, which is actually the only kind of differential equation that we see in this module. But we'll make precise what that terminology means. Then we'll review some properties of the derivative. What does the derivative tell you about its function? And we'll use those properties to analyze a population model that we've seen before. As we do that analysis, we'll bring in a couple new concepts. So we'll define what an equilibrium solution is. And as we do that, we'll put together a picture of the overall qualitative behavior of our model, and we'll call that a phase line. Okay, so first the terminology. Suppose y depends on t. In other words, suppose we're looking at a function y of t. Y, of course, is pretty traditional language to use for the dependent variable. I'm using t here rather than x because so often our independent variable represents time. Then if we have a differential equation for the function y, which is an equation relating y and its derivatives, could be y prime, y double prime, etc., then the order of the differential equation is the highest derivative of y that appears. So a first order equation could look like y prime equals 2y plus 7, or dy dt equals 2y plus 7. That's first order because the highest derivative we see there is a first derivative. We could have a second order equation that could look like y double prime equals sine of y. There we see the function, that's actually the argument for the sine function. We don't see the first derivative, but we do see a second derivative. So since the highest level derivative that we see is a second derivative, this would be a second order differential equation. In this module, we're only interested in first order equations. So these are equations where you might have y and you will have y prime. Let's say a little bit more about the form of the equations that we work with. If we isolate dy dt, or y prime of t, everything that's on the right-hand side of the equation, we could just say, let's call that whole right-hand side f of t and y. So if I flip back to my first order example here, f of t and y would be 2y plus 7. That would just be the right-hand side of this equation. In that example, t, the time variable, didn't actually appear. That happens pretty often for us. So if our right-hand side only depends on y, we call that autonomous. So in this module, we are most of the time interested in first-order differential equations which are autonomous. Another note on notation here, I'm using y because again that's a traditional output variable, but we have so far looked at a lot of population models, so we could see p instead of y or something like that, but that's the function that we're interested in studying with our differential equation. So here are some first-order autonomous differential equations that we've seen so far for population models. This first one we know is exponential growth, like bacteria in a petri dish. So in this example, it's first order because we see the first derivative dp dt, and it's autonomous because in this case, f of t and y, or really f of t and p, is just r times p. We'll leave the parameter out of the function inputs because once we've picked a parameter, it's just a constant. For the second example we've seen so far, this is also a first-order autonomous differential equation, and its right-hand side gives us another function which really only depends on the population p. F of t and p is rp times 1 minus p divided by k. I wrote both of these functions in the general form where we have f of t and p, but both of the examples are autonomous. The right-hand side only depends on the population. Okay, so that's just a little bit of vocabulary, and when I throw this out there, it's just because I would like to call these functions by a name, say a first order ordinary differential equation or something like that, but we're not looking at lots of different types of differential equations. We're only looking at these first order kinds in this module where we have, say, a population function and its first derivative. Let's also bring in some facts about derivatives now, and then we'll use that to study that second population model I wrote down on the previous slide. Let's see, I shouldn't use the letter F here because I was using F on the previous slide to represent something different. So let me say G. I just mean y is a function of t. So if y is a function of the input t, then we say that y is increasing whenever the sign of its derivative dy dt is positive. So our outputs are increasing. On the other hand, y is decreasing or going down whenever the sign of the derivative is negative. Those are the two behaviors we're most interested in today, but we could also say that y could be experiencing a local maximum or a local minimum whenever its derivative is 0. Those would be critical points, but again, we're not going to really talk about that much today. I just threw that up there. Okay, so let's return to this model that we've looked at before. So this is a population model which satisfies dp dt equals r times p times 1 minus p over k. So p here is the population at time t, and the rate of change of the population at any moment can be computed like this. So it depends on the size of the population. Here, t is time in years, p of course is our population function, and then r and k are parameters, and we're going to give a little bit more meaning to particularly k in this analysis. Okay, so what we're going to do on the next slide is use the sign of the derivative to just give a nice overview of how this population behaves. So just by looking at the sign of dp dt, we can say a lot about what we would think the population would do over time. As we do that, we'll identify what we want to call equilibrium solutions and put together the phase line. Okay, so let's start by just describing what the derivative looks like for different values of the population. So again, r and k are positive constants. 1, of course, is a positive constant. So the sign of the right-hand side here is going to depend on p. With that in mind, we can actually plot dp dt versus p. So let me put p down here and dp dt up here. We'll just work out kind of like what the sign of dp dt is based on what the value of p is. So this is a population. It doesn't make too much sense to look at a negative population, but what if the population were 0? So if p equaled 0, if we had no members of the species, then dp dt would actually also be equal to 0, and that should make sense to you because if you have no members of the species, you don't really expect that to change. Okay, so when p is 0, p prime is also 0. Now let's think about what if p were a positive number. Well, we have the product of two terms here, so the sign of the product can be determined if we know the sign of the individual components. R is positive, and if p is positive by assumption, rp is always positive. So that first term is not going to affect our sign. What about 1 minus p over k? Okay, I don't have an actual value for k, but let's say k is like 20. So if p were 1, 1 minus 1 over 20 is positive. If it were 10, 1 minus 10 over 20 is 1 minus a half. That's still positive. This will change signs when p equals k. In fact, when p equals k, we get 1 minus 1, which is 0. So if I kind of put k here, we have another place where the rate of change of this population is 0. And then when p is greater than k, p divided by k is a larger numerator divided by a smaller denominator. That's going to be greater than 1. So 1 minus p over k would be negative, so overall the product would be negative. So I did that by looking at the factors, but you could also expand this and realize that it's a quadratic, a degree 2 polynomial in p opening downwards. So we found the x-intercepts, and we could actually sketch this quadratic. It's going to be kind of like this. I'm kind of bad at drawing parabolas. Oh, that wasn't too bad. I'm going to make that arrow. And maybe we don't really need what's to the left of 0 because we're looking at a population. But you could have a function that does go negative. I mean, that could happen. So you could include that if you wanted to. Okay, so between 0 and k, dp dt is positive. Greater than k, dp dt is negative. So to write this out, we could say if the population is between 0 and k, dp dt is positive, so the population will increase. If p is greater than k, then dp dt is negative, so our population is going to decrease. Now, an equilibrium solution for this model is going to occur if we can find a value of p for which the derivative is always 0. So if I plug in p, I get dp dt equals 0. The population will never change. And that's going to happen when p equals 0 and p equals k. So if p is either 0 or k, the derivative is 0, so we don't get any instantaneous change, but we would also just never get any change because dp dt is kind of stuck at 0. As I already mentioned, the equilibrium solution at p equals 0 is really easy to interpret. So if we have a closed population of fish in the tank and the closed population is 0, I just have an empty tank sitting on my desk, I'm never going to have any fish. So dp dt will always be 0. K is a little bit different. That's a little bit more special. So we'll talk about that in a second. But before we do that, let's sketch the phase line. Now what the phase line is a line that you can sketch for an autonomous first-order differential equation that captures the large picture behavior of what's going on. So in particular, what we want to do is identify 0 and k as special equilibrium solutions. And then we just draw arrows to say what happens between those equilibrium solutions. So if I'm between 0 and k, or rather if the population is between 0 and k, it's going to increase. If the population is greater than k, it's going to decrease. And if we were modeling something with p which could go negative, you could also do that it would decrease to the left of 0. So it's kind of like we've taken this picture, which is two-dimensional, and collapsed it into just a single-dimensional picture that gives us the same information. So this phase line tells us how p would change in different zones, basically. Okay, we've seen a model that looks like this before. So if you're smaller than k, you increase to k, but you're never going to cross k because k is an equilibrium solution. So if you're starting down here, you're going to slide closer and closer to k, kind of asymptotically. You never really get there. If you have exactly k members, you would stay there. And if you have more than k members, then your population would actually decrease down towards k. We've seen that kind of behavior. We called it a carrying capacity. So it turns out this differential equation for this population function p of t is the logistic model that we've already seen. So here was an explicit solution to this differential equation. Let's just check that. So how do we check this? I want to see if this function p of t satisfies the equation up at the top, the differential equation. So given this explicit form for P of t, let's differentiate it to put it in the form dp dt, and we'll see if we can kind of simplify and rearrange terms so that it looks like the right-hand side. So given P, what is dp dt? Okay, P is a quotient, so we're going to do low d high minus high d low divided by low low. So low d high, I'll do this slowly, low is going to be p naught e to the rt plus k minus p naught, so that's low, and then d high is just rk p naught e to the rt. Okay, minus high, so minus k p naught e to the rt. D low is actually just rp naught e to the rt. And that's because k and p naught are constants. So the derivative of the denominator is really not that complicated. And then low low is going to be the denominator squared. Word to the wise, whenever you're doing quotient rule, don't expand this until you decide that you have to, because most of the time it's better in factored form. So it's better written as something squared. Okay, I could multiply everything in the numerator out, but actually what I think is smarter here is to try to identify the greatest common divisor of the first part, low d high, and the second part, high d low. So I see, I think I can actually pull this whole thing out, rk p naught e to the rt. So here's the r p naught e to the rt and a k. And I don't think anything else comes out nicely, no. So then we can have rk p naught e to the rt, and when we factor that out of the first term, we're left with p naught e to the rt plus k minus p naught. And then when we factor that out of the second term, we're left with minus p naught e to the rt, and then all over the denominator. Okay, so inside my parentheses in the numerator, we get some cancellation. That's always good to see. And we're left with, I'm going to run out of room, so let me write it to the right. I usually like to go down if I'm working on paper, but on the slides it's a little bit difficult, so go off to the right. Now, what I'm going to do is recognize that k p naught e to the rt right here looks exactly like that. So that's good. And then also, one copy of the squared term in the denominator is the same thing as the denominator for the function. So if I group those two things together, numerator divided by denominator, I could actually call that p of t. And that would simplify at least the amount of stuff that I have to write. So let me bring r by itself out front, and then I'll do the highlighted part from the numerator, k p naught e to the rt, divided by one copy of that term from the denominator. So let me paste it, and then I'll just get rid of that square. And then I'm out of room. Okay, let me just go down to the next line. And then we're left with k minus p naught divided by the other copy of the term in the denominator. And because I see where this is going, I think I'm going to put k minus p naught like kind of over here. I think that's the right thing to do. Oh wait, and then I also need to get rid of the squaring. There we go. Okay, I think that's all simplified now. So as we said, the middle term is just p. That entire expression is really just the form of p of t that we have at the top, so we can replace that. And then for the other term, what I'm going to do is think about what this would look like, and you could write that out separately if you wanted to. In fact, you could stop here and then show that this matches that. I wouldn't try to do both at the same time, like in the same equation. You could do left-hand side, right-hand side. Look, they're equal. But I really like to try to take the left-hand side and simplify it all the way down to the right-hand side. So what I'm going to do is realize that in this numerator, I would like to have something divided by itself minus p over k or something like that. So let me take the expression p naught e to the rt and add it in the numerator and then also subtract it from the numerator so that I haven't actually done anything inappropriate. Okay, so that would cancel out. But now if you look at this part and this part, if I kind of break that numerator up now, I'm going to have that turns into 1. Okay, so I think I will go to the right now. So this is going to be RP times 1 minus P naught e to the RT divided by the denominator, but that's the same thing as P without the K in the numerator. So that's like P over K. Several of the steps in that simplification were obviously motivated by the fact that I knew that this was going to work out, right? So I knew what I was trying to get to, but that's okay. So we do in fact see that P of t satisfies this differential equation. So this is another way of thinking about the logistic model, and I like it better because you get a better picture of what's going on. If I just eyeball this function, it's a lot harder for me to see like what's really happening there. So in particular, with that differential equation, we can put together the phase line, which is really like the most interesting part of the logistic model, is realizing that you have this carrying capacity, and if you're smaller than the carrying capacity, you're going to grow towards it. And if you're larger than the carrying capacity, your environment cannot support the population, so you're going to decrease down toward the carrying capacity. There's another nice feature of the logistic model that's probably a little bit easier to see if we're working with the differential equation, and that's the value at the point of inflection. So you may have observed that the point of inflection, when your logistic model stops, kind of increasing at an increasing rate and starts to slow down towards that carrying capacity right around here, that happens at k over 2. It's just a nice symmetry that you see in the graph of the logistic model. Now we can actually find that value k over 2 using the differential equation for the logistic model up at the top, because the point of inflection is going to happen when the second derivative, p double prime of t, is 0. Now I usually write p double prime for a second derivative because it's a lot more concise, but if you wanted to write the second derivative using this kind of Leibniz style, this is how you would do it. Okay, so what is that second derivative? What we are not going to do is differentiate this twice, because that would be a mess, and it's easier if we go ahead and start with what we know is the first derivative and differentiate that. So we'll take the derivative of this right-hand side with respect to t, keeping in mind that p depends on t, but r, 1, and k are constants. So wherever I see p, I'm just going to put in p prime and that sort of thing. So we have product rule. That's going to be rp prime 1 minus p over k plus rp and then negative p prime over k. You could expand that, but similar to what we did a minute ago, I'm going to pull out a greatest common divisor for both of these. So I can see rp prime in both expressions. So let's pull that out, rp prime. And we're left with 1 minus p over k minus p over k. Okay, so that's rp prime times 1 minus 2p over k. If the product of two terms is equal to 0, then one or the other is 0. So either rp prime is 0. Since r is a positive constant, that means p prime is 0. Which, based on our previous analysis, means that either p is 0 or p is k. For both of those, we know the population is flat, so that's not where we're going to find a point of inflection. Or, and this is what's going to have to be 0 because we know that we didn't get a point of inflection over on the left, we could have 1 minus 2p divided by k equal to 0. So that means k equals 2p. Or in other words, p is half the carrying capacity. And that's what we expected to see. So this is an example of a calculation which I think is a lot cleaner and more elegant if you start with the differential equation for the logistic model rather than this explicit expression. Okay, let's set the logistic model to the side for a minute and talk a little bit more about equilibrium solutions and phase lines. So again, here's the style of first order differential equation that we're looking at. And we say that we have an equilibrium solution for such an equation if we can identify a value of y, the output, for which the derivative is always 0. Not instantaneously 0 and then it changes or something like that. We're looking for equilibrium, a value of y which never changes. Like for the logistic model, if we have no members of the species or we're at the carrying capacity, those solutions never change. Those are equilibrium solutions. So here's an example of a model that's just kind of put together with some algebra. So find the equilibrium solutions for dy dt equals y times 10 minus y times 20 minus y. And then we'll sketch the phase line. We'll use that phase line just to read off the long-term behavior given different initial conditions for this, say, population or whatever y is measuring. It could be concentration of salt in a fluid or something like that. Okay, so what values of y make dy dt always 0? Because our dy dt is written as the product of three terms, we can see that there are three such values: y equals 0, y equals 10, and y equals 20. That's the roots of the right-hand side. So if this were a population model and we had 10 members of the species, then dy dt would be 0, and it would stay at 0. So let's put together the phase line. Okay, so we have 0, 10, and 20 as our equilibrium solutions. To figure out the big picture behavior at every other possible value of y, we just want to determine the sign of dy dt to the left of 0, between 0 and 10, between 10 and 20, and then to the right of 20. Now, if we know the sign between 0 and 10 at one particular value, like 5, then we know it for the whole region. Because if dy dt had changed signs again during this region, we would have picked up another equilibrium solution. So you just need to find one representative sign for everything between 0 and 10. All right, if I plug in 5, we get positive, positive, positive. That's a quick way of doing it when your right-hand side is in factored form, right? I don't really need to know that 10 minus 5 is 5 and 20 minus 5 is 15 and 5 times 15 is, I don't know, times 5. I don't really care about the exact number. I just need to know the sign. So if you plug in 5, you get positive times positive times positive. Which means that between 0 and 10, we're traveling to the right. So the quantity y would be increasing. I skipped to the left of 0. Let's go back and do that now. If y is to the left of 0, we would have negative, positive, positive. Overall, that product would be negative and we would be decreasing. What about between 10 and 20? We'd have positive, negative, positive. So the product of those three terms would again be negative. And then greater than 20, it's positive, negative, negative. So the product of those three terms would be positive. With this phase line, just this simple snapshot of how y behaves at its equilibrium solutions, and then between them, we can give long-term forecast given different initial conditions. So if y of 0 equals 3, suppose our initial population is 3, that puts us here on our phase line. What we would predict is that over time, y would grow towards 10. So we can say if y naught equals 3, then the limit as t goes to infinity of y of t equals 10. On the other hand, if our initial value of y is 14, that puts us about here, we would decrease to 10. So maybe to distinguish that from the first case, I could write y would increase towards 10, and then if y at time 0 is 14, y would decrease towards 10. If y is 40, that puts us to the right of 20, we would increase. Okay, so I hope that helps illuminate how you look for equilibrium solutions and put together the phase line. Let's finish today by taking our logistic model and changing it a little bit. So this is exactly the same as before. Same time and years, P's population, R and K are positive parameters, except I've put a negative sign. So let's analyze this model, and I think we can do this all at once by just creating the phase portrait. Okay, so just like with the logistic model, we would have zeros for dp dt when p equals 0 or p equals k. So 0 and k are still our equilibrium solutions. This time, however, if we were between 0 and k, we would have negative times positive. So we would actually reverse the sign compared to the logistic model and travel to the left. Similarly, we would reverse the sign if we were greater than k. We would have negative times negative, this would be positive. And just for good measure, if we were to the left of 0, if that was realistic for p, we would be positive. So for this population model, we have a totally different outcome for our population. It's not going to be like the logistic model. If we're between 0 and k, our population dies off. It's like we haven't reached some viable threshold for the population. The population is too small to continue. However, if we have more than k, if we've crossed some minimum level for this population, then we grow. And it turns out we actually grow very quickly. This product just gets larger and larger as p grows, so to the right of k, we actually end up with explosive growth. The population right at k is a little bit strange because if the population were exactly k, it would stay at k forever. That's a little bit harder to picture with this description than with the true logistic equation where you have a carrying capacity, and that carrying capacity kind of makes sense as a threshold. It's hard to imagine that a population would either be exactly k or explode. But in this case, this k here, it's not as meaningful. It's more like defining two zones for the population. Either it's not large enough to thrive or it really thrives. Okay, that concludes this lecture. Thank you for your attention.